everyone, today we're going to be presenting our progress on our weather forecasting project. Our main goal is to develop predictive models for weather and climate change in a given city, with possibly identifying a twin city that has a similar climate for each city in our future steps. So far, we've tested classification and regression models, and we're currently working with time series to improve prediction accuracy. As a baseline, we worked with Boston Weather Daily Summaries dataset.
It consists of daily summaries from 1970 to the present. As you can see, we have 45 different features here, but a lot of them have missing values, so we're going to end up dropping them. We first set up an index by the date and drop all non-numeric columns. Out of the columns that are left, we take the ones that have at least 90% of their data filled in. Any missing values that still remain, we're going to fill them in using context from adjacent days. Now going down here, we just have a quick check to make sure this temperature data is kind of lining up with what we'd expect. And then we have the precipitation down here. The base question we're going to first ask ourselves is, given all of these features for today's weather, can we successfully predict tomorrow's max temperature and whether or not it's going to rain tomorrow? So to do this, we're just going to tack on two features to the end of our data set. We want to do a quick check of our features to make sure that they're correlated with the response variables so that we can actually make successful predictions, and also that they're not too correlated with each other so that we don't have redundant features.
Before jumping into our models, it's important to note that if our model just guessed tomorrow's max temperature using today's, it would be off by about 6.7 degrees Fahrenheit. Likewise, for a precipitation prediction, this baseline would be correct 62% of the time. Hopefully, our models are able to improve on these benchmarks. To facilitate testing our models, we wrote a backtest function, a way to verify that our future forecasting would be correct by validating it on past data. We take in a temperature model, which is a regressor, and a rain model, which is a classifier, as it is a binary indication of if it rains or not. For each iteration, we train our models on all preceding data and test on the next 90 days. We train both k-nearest neighbors regressor for tomorrow's max temperature and classifier for the precipitation. To find the best end neighbors value, we ran a grid search from 1 to 150, eventually landing on 70 for temperature prediction with a mean absolute error of 6.31 and 80 for rain prediction with a mean absolute error of 0.34.
Looking at our results now, we see that each of our models had a slight improvement over the baseline. In particular, the best models look to be XGBoost and gradient boosting. Looking down here, we can see all of our predictions over a year. Keep in mind that each model is not predicting the whole year, but instead it's given yesterday's temperature and now predicting today's temperature. Similar thing with rain, where at the top we have predictions of rain and at the bottom we have predictions that it will not rain. You have probably noticed that our previous models were missing a critical component: seasonality. As you can imagine, if we were forced to extend our predictions, not just from tomorrow's weather, but to next week's or next month's, they'd become more and more divergent from the actual weather. If we can fit a part of our model to the seasonality itself and cancel it out, we can use the rest of our model to fit to the remaining linear trend. So, how are we going to add the seasonality component? With Sarimax, this relies on a few different hyperparameters. First of all, we have our autoregressive order, the AR, which is the number of past values used to predict the current value. Second is the differencing, which is a mechanism used to remove noise so we can focus on the overall trend. Next, we take into account the moving average, the MA, which will let us keep track of past errors so we can learn from them. Next, we have the same parameters but for the seasonality, and a step, which in this case will be 365, divided by the sample factor because I took a subsample of this just to make training quicker. Now let's jump into some of the results. In this first case, I trained on 20 years and then tested on another 20. As you can see, towards the end, we're getting increasingly further off, and this is an average error of 18 degrees Fahrenheit, so pretty off. But if we're able to train for 39 years and then just test on 1 year, we're back down to about the same error that we were at with the previous models. But keep in mind, in this case, we have to predict a whole year, and the previous models just had to predict 1 day. Finally, I tested on just 1/10 of the year, and now we can see that we're really getting some nice performance with just 2 degrees Fahrenheit error. Moving forward, we're going to continue experimenting with the time series models that we've used and also incorporate some deep learning into the mix. We're going to look at more cities rather than just Boston so that we can implement our Twin Cities idea. Thanks for watching.